Good morning, dear students. Today we are going to discuss about conformations of monosubstituted cyclohexane. We know that what you meant by ring flip. At room temperature, the interconversion between the two chair conformations of cyclohexane is very rapid, and during this process all axial bonds in one conformation become equatorial in the other and vice versa. This is called a ring flip, and both conformations are equivalent and of equal energy. So they cannot be distinguished. However, when one of the hydrogens of cyclohexane is substituted by another atom or group, the two forms are no longer equivalent because the substituent will be in an equatorial position in one conformation, whereas it will be in an axial position in the other. For example, if we replace one of the hydrogen atoms present in cyclohexane by a CH3 group, when we displace hydrogen from this axial position, that is, this is the conformation of monosubstituted cyclohexane. If it is in axial position, after ring flip, it will convert it into equatorial position. This is another conformation of monosubstituted cyclohexane after ring flip. Here we can see that in one conformation, CH3 group is in axial position, and after ring flip it will convert it into equatorial CH3 group. So, which conformation is more stable? Here both conformations are not equivalent, not in equal energy. Then which conformation will have more energy, or which conformation is more stable? Here, when the substituent present at equatorial position, that will be more stable. And the substituent when it is present at axial position, that is less stable. Why it is less stable? Here, when the substituent present at axial position, there will be an interaction between axial hydrogen, that is called 1,3 diaxial interaction. 1,3 diaxial interaction. That is, this is first position, this is third position. So, this is 1,3 interaction, 1,3 axial interaction. And this is again axial hydrogen, there will be also an diaxial interaction. The interaction due to two axial substituents, two axial groups are called diaxial interaction. And this hydrogen, axial hydrogen at fifth position, so it is called 1,5 diaxial interaction. The repulsive crowd or steric interaction between two axial substituents or two axial atoms or groups are known as diaxial interaction. When the diaxial interaction at first and third position, it is called 1,3 diaxial interaction. If it is first and fifth position, it is called 1,5 diaxial interaction. Whereas if CH3 group at equatorial position, there will be no steric interactions because the group at C3 and C5, that is the axial hydrogens present at C3 and C5, these groups are far away from the equatorial CH3 groups. So, equatorial methyl cyclohexane is more stable than the axial methyl cyclohexane. Equatorial CH3 groups or equatorial substituents does not experience any steric crowding from the axial hydrogen. The energy difference between the two conformation is only 7.5 kilojoule per mole at room temperature, and this energy barrier is too small to prevent the interconversion between them. So, the individual components cannot be isolated. The equilibrium mixture contains predominant conformation of equatorial methyl cyclohexane. Methyl cyclohexane, equatorial methyl cyclohexane will be more stable. Next is, how can you assign cis and trans isomerism in cycloalkanes? Consider the case of cyclohexane, and we can draw the conformation of cis 1,4-dimethyl cyclohexane. How can you draw the conformation of cis 1,4-dimethyl cyclohexane? We know that what you meant by cis, what you meant by trans. If the two substituents are in upward or in same phase, on same phase of the ring, it is called a cis conformation. If both the substituents are in opposite sides of the ring, that is called a trans isomer. Then we know that in case of cyclohexane, which is more stable, chair conformation is more stable. So we can draw the chair conformation of cyclohexane. Then we can assign first and fourth position as methyl groups. So this is first position. Consider this is our first position. 1, 2, 3, 4. And this is fourth position. And there will be two methyl group. Methyl group can be either in axial position or in equatorial position. Anyway, the conformation will be cis. So, in order to attain cis conformation, both the substituents will be on same side. So, if CH3 group in axial position, how can you draw cis conformation of this substituent? Here also CH3 group should present at upward relative to the cyclohexane ring. So, the upward position will be equatorial. So, one CH3 group will be in equatorial position. That is, this CH3, axial CH3 group in upward. Here also, equatorial CH3 group is also upward. So, both substituents are upward. This is called a cis conformation. And 1, 4 are the positions of CH3 group. And the substituents are 3, 2 methyl groups. So, dimethyl cyclohexane. This is the structure of cis 1,4-dimethyl cyclohexane. Here one sub CH3 group at axial position and another CH3 group at equatorial position. Then how can you draw trans conformation of 1,4-dimethyl cyclohexane? So trans means both the substituents are in opposite phase. So if one CH3 group at equatorial position, that is towards upward, and here CH3 group should be downward, that is trans. So if we replace this hydrogen by CH3 group, we get trans 1,4-dimethyl cyclohexane. Here one CH3 group at a downward and here it is upward. So this is called a trans. Here we can see that both the CH3 groups are at a equatorial position. So this will be more stable conformation of 1,4-dimethyl cyclohexane. So trans 1,4-dimethyl cyclohexane is more stable than cis 1,4-dimethyl cyclohexane. Why? In the case of trans 1,4-dimethyl cyclohexane, both the substituent CH3 groups are at a equatorial position. There is no diaxial interaction. Whereas in the case of cis 1,4-dimethyl cyclohexane, one CH3 group at axial position and another CH3 group at equatorial position, and there will be 1,3-diaxial interaction in the case of axial substituents. So trans 1,4-dimethyl cyclohexane is more stable than cis 1,4-dimethyl cyclohexane. If this conformation undergoes ring flip, both the CH3 group will becomes at a axial position, and that is least stable conformation of 1,4-dimethyl cyclohexane, in which both the CH3 subgroups are at a axial position. Next is conformation of ethane. For ethane molecule, that is CH3, free rotation about the CC sigma bond, carbon to carbon sigma bond, gives rise to an infinite number of spatial arrangements. Infinite number of spatial arrangements in which the relative positions of the hydrogen atoms on the two carbons are different. These represent the infinite number of conformations of ethane. Of this infinite number of conformations, two extreme cases are: one is staggered conformation of ethane. Second one is eclipsed conformation of ethane. What do you mean by staggered conformation? In staggered conformation, the hydrogen atoms on one carbon are situated as far apart as possible from the hydrogen atom on the other carbon. Whereas eclipsed conformation, in which hydrogen atoms on one carbon are so close as possible to the hydrogen atoms on the other carbon. Then the infinite number of possible conformations intermediate between the two extreme cases are called skew conformation. Skew conformations are intermediate conformation between two extreme conformations. Then how can you draw the conformation of ethane? We have different representation, that is two-dimensional or planar representation of conformation of ethane molecule. First one, flying wedge representation. 2. Second one, Soho's representation. Third one, Newman projection. This is the flying wedge representation of ethane. Flying wedge representation is also known as wedge and dashed line representation, or it is called perspective formula. Here, three types of notations are used. Solid line represents a bond connecting two carbon atoms lying in the same plane of the paper. Wedge, this is wedge representation. Wedge are used to represent bonds above the plane of the paper, and dashed line or broken line stand for bonds lying below the plane of the paper. And this is the flying wedge representations of the staggered conformation. Here both hydrogen atoms are opposite phase, and this is eclipsed conformation representation of ethane. Here both hydrogen are same phase. This is Soho's formula of ethane. This is staggered conformation and this is eclipsed conformation. In Soho's projections, the observer views the molecule slightly from above at an oblique angle from the right, and it is projected in the plane of the paper. Here, the bond between two carbon atoms is drawn as a line slightly tilted to the right and slightly elongated than the rest. Here the two carbon atoms can be shown at the two ends of the line. This is one carbon atom and this is one carbon atom. The lower left hand carbon, that is, this is lower left hand carbon, it is considered at the front carbon, and this carbon considered at the back. That is, the upper right hand carbon can be considered at the back and left hand carbon can be considered at the front carbon. So this is front carbon and this is back carbon. Three lines drawn at an angle of 120 degree. This is the angle 120 degree to each other, and attached to each carbon connect that carbon to three groups or atoms around it. So here the bond angle will be 120 degree. This is the staggered conformation. Here both hydrogen, here this hydrogen and this hydrogen are opposite phase, and whereas in the case of eclipsed conformation, this hydrogen and this hydrogen are in same phase. So it is called a eclipsed conformation, and here it is called a staggered conformation. All the hydrogen atoms are far apart from each other in the case of staggered conformation. Next is Newman projection formula. This is staggered conformation of ethane and this is eclipsed conformation of ethane in Newman projection formula. In Newman projections, the molecule is viewed along the bond joining two carbon atoms. The nearer carbon atom of that bond is represented by a point. This is nearer carbon atom, and the bonds to the three groups attached to it are represented by straight lines. These three straight lines at 120 degree to each other. Then the farther carbon atom. Further carbon atom is shown as a circle. This circle represented farther carbon atom. The bonds to its three attached groups are shown as three shorter lines to its periphery. The two are then superimposed to give the Newman projection formula. This is the staggered conformation. Here all the hydrogen atoms are far apart, whereas this is eclipsed conformation. Here the farther carbon atom, this is the bonds to the farther carbon atom. All these hydrogens are nearer to the nearer carbon atom. Now we have to consider the stability of staggered and eclipsed conformation of ethane. We know that staggered conformation of ethane is more stable than eclipsed conformation. Why? In the case of staggered conformation, the hydrogen atoms on the two carbons are situated at maximum possible distances apart. While in the case of eclipsed conformation, the hydrogen atoms on the two carbons are so close to each other as possible. Consequently, the repulsive interaction forces between sigma electron clouds of the CH bonds will be minimum in the case of staggered conformation and interaction will be maximum in the case of eclipsed conformation. Therefore, staggered conformation has a lower energy and more stable than eclipsed conformation. This is the potential energy diagram of the ethane. Here, the energy difference between staggered and eclipsed conformation is 12.6 kilojoule per mole at normal temperature. And this energy difference is known as torsion barrier. This energy difference is not sufficient to prevent the rotation about carbon to carbon bond. That is, this energy barrier to rotation is too low to prevent the interconversion between conformations. So, the individual conformers cannot be isolated. Then, any other conformation of ethane in between two extremes, that is staggered and eclipsed, is known as skew conformation. However, the most stable conformation will be staggered conformation. Next is conformations of butane. This is the skeleton structure of butane and this is the structure of ethane. What is the difference? Here we consider the free rotation about this carbon to carbon bond and resulting infinite number of conformations. In the case of butane, we consider free rotation about the central carbon atoms, that is C2C3 carbon atom. That is, we can compare with the ethane and butane. Here only one substituent is different. In the case of ethane, one carbon attached with the three hydrogen atoms, whereas in the case of butane, one carbon atom, central carbon atom is connected with the two hydrogen atoms and one CH3 group. That is the only difference. So, we can consider the free rotation about C2C3 single bonds and resulting in finite number of conformations same as our ethane. This is the fully eclipsed conformation of butane. Here fully eclipsed means both the bulky groups are in near phase. That is fully eclipsed conformation. Completely sterically hindered conformation. That is fully eclipsed conformation. When this conformation rotates 60 degree, what will be another conformation? This conformation is known as Gauche conformation. Here, the angle between two substituents on the front carbon atom and back carbon atom in the Newman projection formula is called dihedral angle or torsion angle or torsional angle, and it is represented by theta. So, what do you mean by dihedral angle? The angle between a hydrogen atom or a substituent on the front carbon atom and a hydrogen atom or a substituent on the back carbon atom in the Newman projection of a conformation is called dihedral angle. So, dihedral angles are the angles between two bonds on adjacent atoms when we look at a Newman projection. When dihedral angle is 60 degree in a specific conformation, it is called Gauche conformation. So, in the Gauche relationship, two substituents on adjacent carbons are 60 degree apart in the Newman projection. Then, if the dihedral angle is 180 degree in a specific conformation, it is called anti-conformation. That is a staggered conformation. Gauche and Anti conformations are collectively staggered conformations, and this is our eclipsed conformation. In eclipsed conformation, it experiences a torsional strain. What do you mean by torsional strain? Torsional strain is the strain experienced by a molecule when atoms or groups are close enough for their electron clouds to repel each other. That is called a torsional strain. When we rotate again 60 degree to this Gauche conformation, it will convert it into eclipsed conformation. So here total degree of rotation is 120 degree. Here it is eclipsed conformation. When we rotate again 60 degree, that is its converted total degree of rotation will be 180 degree. That is called anti-conformation. That is fully staggered conformation. Here all the substituents, bulkier substituents are maximum apart to each other. That is called a staggered conformation. Here the rotation can take place by fixing front carbon and rotate the back carbon. That is the form of rotation. When we rotate again 60 degree, it will convert it into eclipsed conformation. Here total degree of rotation is 240 degree. When we rotate again 60 degree, it will convert it into Gauche conformation. Here the total degree of rotation will be 300 degree. So it has total 6 conformations in which 2 conformations are Gauche forms. This is one Gauche form and this is another Gauche form, and 2 eclipsed forms. What are the eclipsed forms? This is one eclipsed form and this is one another eclipsed form. and it consists of fully eclipsed form and fully staggered form. Fully staggered form is called anti-conformation. Which conformation will be more stable? Obviously, fully staggered conformation, that is anti-conformation, is more stable than all other conformations. Here two Gauche forms are non-superimposable mirror images of each other. Similarly, two eclipsed conformations are non-superimposable mirror images. Two conformers which are non-superimposable mirror images of each other are called conformational enantiomers. If two conformers of a substance that are not non-superimposable mirror images of each other, they are called conformational diastereomers. For example, anti-form of butane is a conformational diastereomer of the Gauche form. This is the potential energy diagram of butane. It shows more stable conformation is anti-conformation, and then Gauche conformation, then eclipsed conformation, and least stable is fully eclipsed conformation. In anti-conformation, there is no repulsive interaction between the hydrogen and substituents. Here we know that Gauche form is also a staggered conformation, but it has torsional strain. That is, so it has slightly high energy than our anti form. Why Gauche form is more energetic than anti form? Here in case of Gauche conformation, it suffers steric strain due to the bulky CH3 groups. So, Gauche forms are less stable than anti-conformation, even though they are staggered conformations. So, this interaction is called Gauche interaction. Then, why eclipsed conformations are less stable than Gauche conformation? We know that eclipsed conformation, in the case of eclipsed conformation, again there is repulsive interaction due to torsional strain than our Gauche form. So, eclipsed conformation is less stable than Gauche conformation. Then in the case of fully eclipsed conformation, it has highest energy and least stable conformation. It's due to torsional strain and steric crowding of two bulky CH3 groups. The energy difference between anti and fully staggered conformation is 22.2 kilojoule per mole. But this energy difference is not sufficient to prevent the rotation about carbon to carbon bond. So, we cannot isolate individual conformers separately. That's about conformations of butane. So, here we discuss about conformational isomerism. We know that stereoisomers can be classified into two categories. One is configurational isomer, second one is conformational isomer. Configurational isomer can be again classified into optical isomers and geometrical isomers. Optical isomers we discussed in previous classes. Here we discuss about conformational isomers. What is the difference between conformational isomers and configurational isomers? Any of the different spatial arrangements of atoms or groups in a molecule that arises from free rotation about a single bond is called a conformation. Whereas What do you mean by configuration? The specific spatial arrangement of atoms or groups that characterizes a particular stereoisomer is called its configuration. So, conformation involves free rotation about carbon to carbon single bond, that is conformational isomers. And the interconversion between conformations is generally easy and fast. That's about conformations. Hope it is clear. Thank you.